constraints I want to satisfy. Now, I know that the solution has to be of this form. So let me look at all distributions of that form. And that's going to be a curve like this. Okay? And now I find the one distribution of that form that actually satisfies these constraints. And that's the I projection. That's the projection of pi onto the affine subspace. Okay? And we can check dimensionalities over here. Right? The dimension of the whole space, if I have 50,000 words, the dimension of the whole space is 50,000 minus 1. It's minus 1 because they all have to add up to 1. So there's that extra 1 degree of freedom is taken away. So it's 49,999. So the dimension of this whole thing is 49,999. Okay? What is the dimension of this subspace? Well, the subspace is defined by k constraints. Each constraint reduces the dimension by 1. Okay? Each constraint, so the dimension of this subspace is s minus 1 minus k. Okay? So it's k less than the dimension of the whole space. So this subspace has dimension 49,999 minus k. And now what is the dimension of, and we know it's a linear subspace, or sorry, an affine subspace. Affine just means linear, but not necessarily through the origin. Okay? And now, what does the space of distributions look like? Well, it's not a linear set. Okay? It's, there's no reason why this thing would be linear. It's parameterized by a k-dimensional vector. Therefore, it's a k-dimensional space. Okay? And in fact, it's a k-dimensional manifold. So we have this manifold of exponential family distributions. And you can see that the dimensions just add up perfectly. The manifold has dimension k. The constraints have dimensions s minus k minus 1. And these add up to the full dimension. Okay? So there's this unique point of intersection over here. And that's the I projection. Yeah. Pi is on the line because when you substitute eta equals 0, you get pi. You see, if you substitute eta equals 0, then this part drops out. And we know pi already integrates to 1. So the normalization must be 0 in that case. So pi is, yeah, all we know is that pi lies on this line, and p star also lies on this line. Okay. So this is one of the, so these two are sort of perhaps the, two very basic pictures of information geometry. Okay, we're doing very simple operations after all. Even though we started from this other context where, we wanted to fit some distribution over a large set corresponding to constraints, it turned out to be just a simple projection operation. We have a point which is our prior, and we just want to project onto a linear set. Okay, so it's the simplest thing in the world, right? The only hitch is that the distance we're projecting with respect to is not the one we're used to, right? It's this kind of weird KL distance, and that changes things. But what we are finding already that luckily doesn't change things too much. We still have a Pythagorean theorem, and now we have this, nice characterization of this point of intersection. Okay, so it's the unique intersection of the subspace defining the constraints and the manifold of distributions. Okay. Why is there a unique point? Why can't there be many points? Well, we saw that. Okay, so this is, so we saw that this function g prime, we saw that the function between the expectation parameters and the natural parameters, it's a one-to-one mapping. Okay, so given an expectation parameter, there's just one natural parameter that it can correspond to. This is actually assuming that the exponential families are minimal. It's possible to create exponential families with redundancy, by, for instance, copying the same feature over twice. Okay, but assuming minimality, there really is just a unique point of intersection. Yeah.
How should families, the Higgs distribution, the Higgs measure need not be a probability distribution, right?
It need not be a probability distribution, but in the context we're looking at, the base measure, we are starting with a probability distribution. That's our prior. In our context, it is. Yeah. Okay. So, so let's summarize what we've said. Okay. We found a relation between maximum entropy and maximum likelihood in exponential families. Okay. So what we're saying is that when you have a bunch of data points, and you just measure some. So you collect a bunch of data, right? These are maybe the few words that you sampled, the few English words that the alien came across. And the alien noticed a few features, just took down a few things about lengths of words, etc. The following are now equivalent, okay? It's equivalent to say that P star is the projection of that distribution onto the constraints, okay? In other words, P star is the distribution that minimizes the distance to the prior and satisfies those constraints. That is the same as saying that P star is the maximum likelihood distribution in Q to fit the data. Okay? And that's also the same as saying that P star lies in the intersection of the constraints and the manifold of these distributions. Okay, so these are three equivalent characterizations of this I projection P star. Okay. So let's look at an algorithm for doing this. Okay, so far we have this thing, I projection has all these nice features, but how do you compute this thing? How do you go from pi to P star? Well, we've seen it's a convex optimization problem. So one thing we can do is to just give it to some package. There are these packages that claim that they're going to solve them. You just feed it the problem and ask him to do it. Or you can use things like gradient descent methods. Right? So those are very general purpose methods that can be brought in to solve this problem. But now let's look at, but maybe by exploiting the geometry of this, we have all these nice things. This is not just any old convex optimization problem. It's a simple projection. We have the Pythagorean relation. Is there some way we can exploit this to actually come up with an algorithm that is not all that complicated? So here's one. So I think this is due to Chijar. Okay, and I think it's called iterated I projections. So here's the goal again. We have some prior, and now we'll just talk about it in geometric terms, right? We have this prior we want to project onto this subspace that defined by our constraints. So we want to project onto this subspace, okay? And we want to project it with respect to KL divergence. The problem is that this is actually a k-dimensional problem, okay? In effect, I'm looking for the exponential family member that satisfies these constraints. And that's a k-dimensional problem because the eta I'm looking for is k-dimensional. So rather than doing a k-dimensional search, is there some way to reduce it to a one-dimensional problem? And the way you can do that is instead of looking at all the constraints, instead of looking at all k constraints, let's just look at one of them. Let's just try and satisfy one constraint at a time. Okay, so let's just look at the constraint number I, which is this linear subspace. And now, if you just had one constraint, it would be a one-dimensional problem because you're just looking for one parameter eta. That's much easier. If it's just a one-dimensional problem, you can use line search or something like that. So here's the algorithm. Your initial value of P, it's going to be an iterative algorithm. You start with P equal to your prior, and now you keep adjusting P, okay, until you finally get to the I projection. And here's what you do. It's very simple. You just take whatever you currently have, and now you project it onto the next subspace. Okay, so you just keep cycling through all the subspaces. You have k constraints. You have these k. You now have these k separate hyperplanes, and you want to satisfy all of them. In other words, you want to be at the intersection of all those hyperplanes. Right? You want to project to that intersection. So what you do is you just project onto one of them, then you project onto the next, then you project onto the next, and you just keep cycling through these k things. Okay? And somehow this should work, right? So let's see why this thing might work. Okay? So let's look at these problems. Okay? So for instance, let's say they're just two subspaces. Okay? So then we want to get somewhere in their intersection. We want to get there. Okay, to the intersection point. We start with any old pi, and now instead of projecting onto the intersection of the two subspaces, which would be L, we just project onto one of them. Okay, but now it's far away from the other. Now we project onto the next. Now we project onto the next one, and so on. And we keep going back and forth until we get to the intersection. Okay? So how complicated are these projection operations? Well, projecting onto just one of these constraints is really easy. We just have to, projecting onto one constraint, when we just had one constraint, It means that we are looking for an exponential family that just has one parameter. Okay, there's just some eta I. So we want to project our current distribution P sub t, and we want to project it so that it satisfies the ith constraint. So in other words, the thing we're looking for is something of this form, where eta I is just one real number. So that's quite easy. We're just looking for the thing of this form that has the right expectation. We can just do a search for this. Okay? And so, and so we get these simple one-dimensional problems. And the question is, why does this thing converge? And the way you can see that is, well, all we have to do is to prove that we're actually making progress on each iteration. And if you look at the iteration, let's say I'm at P sub t, and the next one, and what I'm doing is I'm cycling between these constraints, right? Let's say the thing I'm currently doing is projecting onto the ith constraint, projecting onto L sub I, right? So I take P sub t, I project onto P sub t plus 1. And this is my ultimate goal, P star. I know P star lies on this thing because P star satisfies all the constraints. Therefore, P star must lie on L sub I. Okay? So now I'm claiming that I've actually moved closer to P star. And why is this? This is just by the Pythagorean theorem. That's the hypotenuse, and this is one of the legs of the triangle. Okay? So on each step, even though, so this seems, so you have these k constraints, and one would think, if you're just projecting onto one constraint, you might totally mess yourself up with respect to the other constraints. But you don't have to worry. Because of the way this Pythagorean theorem works, you can be sure that even if you're just doing one constraint at a time, you're always moving closer to the final distribution. Okay, so this is an example of the kind of, the sort of kinds of arguments that come up in information geometry. Okay. So I'm almost, let me sort of wrap up. What are some other methods for I projection? Well, the one I told you about, although it's a very nice method, I don't think it's the one that actually gets used. So this would be considered a sequential method. This is a method where you only update, so you're looking for an exponential family distribution with k parameters. And what you're doing is you're just updating one parameter at a time. You're just projecting onto the ith constraint. Right? So it would be considered a sequential method. There's a method called iterative scaling, which is a parallel method. It updates all the parameters at the same time. And the remarkable thing about that method, I'm not going to go into the theory of that, but that's also a beautiful method for in a different way, which is that, so this particular method, in the one we saw, you update one of the eta i's, and then you update the next. You cycle through the different eta i's, but at each stage, you actually have a fully normalized distribution. In iterative scaling, there's much that you don't worry about normalization. You update all the parameters in a very intuitive way. It's kind of, if you only cared about that parameter, how much would you update it? You update it in that way. And so the result might not even be a probability distribution. It might not lie on the simplex. So while iterative scaling is running, you're creating these distributions that actually, if this is your simplex, it goes outside the simplex. But you can show that eventually it comes back and it reaches the optimal. It reaches the I projection. There are many variants on iterative scaling, and one can use sort of gradient-based methods as well. Okay, and these are, I think there's many people suggest that these are faster. Okay, so let me wrap up by just talking about a little bit about Bregman divergences. Okay, so one thing we found over here is that we found these strange connections between Euclidean distance and KL divergence. Okay? On the face of it, one would think that they have nothing in common. Squared Euclidean distance is the most well-behaved thing. It's always bounded. If we're dealing with bounded distributions, this thing is bounded. It's very familiar. KL divergence seems so much more wild. It's unbounded. It's not symmetric. However, these two distributions have a lot in common. They both satisfy this Pythagorean theorem, for instance. They both have a very nice notion of projection. So what's the commonality over here? Are there other distance measures that also have these properties? And it turns out that there are. There's this whole family of distributions, of distance measures, called Bregman divergences. And all of these have these same nice properties, these common properties that we've observed, just coincidentally between squared Euclidean distance and KL divergence. Okay? So all these distributions satisfy a Pythagorean theorem when it comes to projection. So what are these Bregman divergences? Well, the way you can think about them is by returning to exponential families. Okay, and then that sort of explains what these things are. If you look at the Gaussian, the natural distance measure for the Gaussian is squared Euclidean distance. I'm talking about a spherical Gaussian. And this is because if you look at the distribution of a spherical Gaussian, it lies in these spherical contours. A Gaussian lies in, if you look at the contours of equal density for a Gaussian, it's these concentric spheres. So the natural distance measure for a Gaussian is just the squared Euclidean distance. You can tell the density of a point by measuring its squared Euclidean distance from the center of the Gaussian. Now, you can define a similar measure for other exponential families as well. For any exponential family, you can say, let me look at the mean of this family. And now, let me look at the surfaces of equal density as I move away from the mean. What distance measure is defined by those surfaces? And that's a Bregman divergence. It turns out that if you look at the multinomial distribution, you get back the KL divergence. And when you look at, and now when you vary the exponential families, exponential families are, incredibly things. They include undirected graphical models. Okay, so as you vary the members of this family, you get all these different distance measures, these contours of equal density, and they're all Bregman divergences. That's what Bregman divergences are, and they all have these nice properties. And it turns out that once you start looking at eye projections, once you start looking at the geometry of these other Bregman divergences, a remarkable number of machine learning tasks that seem to be coming from a totally different place actually turn out to be eye projections. Okay, so for instance, there are papers that show that once you generalize information projection to these arbitrary Bregman divergences, these things like boosting and iterative scaling, these other methods actually turn out to be eye projection operations. The simple algorithms for eye projection with respect to different Bregman divergences. Okay, and so in a sense, this eye projection is a very fundamental, it's a very sort of central operation in machine learning, and it's probably much more widespread than one imagines. So one thing that would be an interesting project would be to just kind of sit down and see whether you can just really write down a lot of machine learning as just simple as either just single projection operations or alternating projection operations. So something like EM algorithm, it might just be a set of alternating eye projection operations. And this would be really cool because then, you might be able to describe a whole lot of machine learning in this sort of meta language of eye projections, right? So these very simple projections, and thereby prove, when you're talking about things, you can prove results in great generality. Talk about the convergence of a method, instead of proving it just for, say, k-means, you could prove it for, a huge family of clustering algorithms that work not just with Euclidean distance, which is k-means, but any other Bregman divergence. So this is, but this is very much an unexplored area. Okay, so that's it. So what's going to take it? So any questions about stuff? Yeah.
One question, formulation, there's a constraint symbol have a special form, EHI equals EI. So I wonder if this formulation can be applied to such constraints like bimodality of distribution.
So what kind of constraint?
Bimodal, for example, Gaussian distribution, two bounds, something like that.
Oh, so what would the constraint look like in that case?
There are two bumps in the density curve.
I don't see that they would. I mean, so you can generalize it a bit, So for instance, it might be a bit much to say, look, I had this prior, I've got these 10 data points, and I observed averages. Now I want to exactly fit those averages. That might be a bit much, You might say that I only want to approximately fit those averages. So instead of getting an exact constraint, You just say that, I want within epsilon or something like that. But then the functional form of the answer remains the same. Yeah?
I just wonder the uniform distribution, a special case of exponential family. Is that the special?
The uniform distribution, so it depends on which one you're talking about. If you look at the uniform distribution in the continuous domain, this is not something that can be expressed as exponential family.
Consider the Gaussian distribution if the feature, if you have only one feature that V is 0 and there is no constraint on covariance, then actually you reduce to the uniform distribution. Is that right?
Yeah, well, so in that case, your base measure is dominating. So, so there's this one, right, so there's this one tricky issue over here. So I was talking mostly about discrete. You see, I was talking mostly about discrete distributions. And you would think, hey, you want to generalize it to continuous stuff, that's no problem, right? You just got to make all the sums, integrals, and stuff. Unfortunately, it's not so. It's really much more complicated than that because even the notion of entropy in the continuous setting becomes a little bit weird. For instance, in the continuous setting, entropy can actually be negative, which it can't be in the discrete setting. And if you look at this axiomatic formulation, well, that only works for discrete distributions. I'm not even sure, whether one can prove that kind. I've not seen that kind of well-foundedness results for the differential entropy. So there are some, I was basically sticking to discrete things because that's where a lot of the theory has focused up to now. And there's some, it's not, the continuous case is not so easy. I mean, there's definitely some technical hurdles. Yeah, in the Gaussian case it was. But, so when one is dealing with exponential families, that's all fine. But when one is dealing with this, when one's actually bringing entropy into it, right, then in those cases I was just sticking to the discrete case. Like, for instance, the example with the words and so on. It's just a discrete sample space. Because... So I'm not sure exactly how much one can extend. But this is something that, this is an area in which I feel the theory is a little bit underdeveloped. And okay. Thanks.